right, this will be the conclusion of the video we started today in class. We had left off on doing an example that was an application. It was this one about the amount of a substance, uranium-240, that was left after a certain amount of time. We're going to do another similar example. This one says, suppose that the velocity, v of t, in meters per second of a skydiver falling near Earth's surface is given by v of t equals, and we have our equation, and this is measured after t seconds. To start with, it says to find the initial velocity. So the initial velocity, just like in our initial problem last time with our initial substance, would be when time is 0. So at the beginning, right? And so this would look like 51, and 1 minus e to the negative 0.25 times 0. Just like the last one, we can work through this pretty nicely in our heads if you want, or you can grab a calculator. Obviously, that exponent is multiplied by 0, so the exponent itself is 0. E to the 0 is 1. So inside the parentheses, we have 1 minus 1, which is 0. So we have 0 meters per second. And if you think about it, that makes sense. If you just started out jumping out of an airplane, which, heaven help you, I don't know why you would do that, but if you did, then you wouldn't be going anywhere yet. Your velocity, your movement, your speed is nothing. Very, very beginning of your jump. Of course, it moves very quickly from there. So on the second one, when it says what's the velocity after 6 seconds, then we have v of 6, right? Now that we're going to need a calculator to calculate. So you can either go piece by piece, right? This is, that doesn't look like a good 6. That's better. That exponent, 0.25 times 6 would be equivalent to negative 1.5. If you don't want to make sure, you have to be careful in those parentheses and so forth. But anyway, you look at this. If you evaluate this and we round to the nearest whole number as it indicates, we're going to end up with 40 meters per second. One more application of this that is really important to notice because it is something so super applicable is compound interest. So if you borrow money on a loan, if you put money in a savings account, this affects you, and that's kind of almost all of us at this point. So in this equation, you'll notice several features. We have some variable names, some letters. A is the amount after t years, so kind of an ending amount or a later amount. P stands for principal. That's the amount you start with. R is your interest rate. That one you have to be a little bit careful of because it needs to be as a number. So what do I mean by that? Well, it means like if you had, let's say, 5% interest rate, this would mean that R equals 0.05, right? The percent that goes along, or the decimal expansion that goes along with the percentage. N is the number of compoundings per year. So if it says annually, that'd be once a year. If it says monthly, that would be 12 times a year. Quarterly, it would be 4 times a year. If it said daily, it'd be 365 times a year, and so on. And then the last one, T, is that it's time in years. Make sure that it's in years, because sometimes, especially when you do financing, like you think about car loans, sometimes they'll say, you're going to get a 60-month loan. Okay, 60 months, but what is that in years? Oh yeah, 5 years. So, make sure we're working in years when we get to time. All right, I have 2 examples of this one. So we're going to do both of them with loans today. Suppose a loan of $8,000 has an interest rate of 9% compounded monthly. No payments remain on the loan. That's how these formulas work, is with no payments. They're just sitting there. The first question is how much is owed after 1 year? So our basic equation here is A equals P for the principal, that's the $8,000 loan, times 1 plus R is the interest rate, which it said it was 9%, so that's 0.09. So it's compounded monthly, that's 12 times a year. And then we have T in time in years, and so that will depend on which problem we're working on. But this is the generic equation for the rest of the work. So we need 8,000. I have 1 plus 0.09 over 12 to the 12 times 1, because it's 1 year. And because this is money, unless you're told otherwise, we're going to round to 2 decimal places because it's money, right? And this one you will find is actually, and we have to make sure we do a dollar sign as well, is actually $8,750.46. Okay. Very similar. How much, I should say how much, is owed after 2 years. So, again, that's the 8,000. 1 plus r 0.09 over 12 raised to the 12, in this case times 2. So it's essentially an exponent of 24. And if you simplify this one, you get $9,571.31. All right, so let's change some of the conditions just a little bit and see what happens with one more example. Suppose you have $2,000 that's loaned at a rate of 18% compounded annually. Assume no payments are made. How much is owed after 6 years? Now, some of you might be looking at it and thinking, "Ooh, 18%, that's really high." And it is really high, but if you take a look really quick, for those of you who have them, it's about what a credit card interest rate is these days. Really high. So, we have A equals 2,000, because that's my principal. 1 plus my interest rate. My interest rate is 18%, so this is 0.18 over n. N is the number of compoundings per year. Now this is annually, so annually means 1. And then raised to the 1 times t for time. Time in years, and this says 6. So I have it raised to the power 6. And if you evaluate this after 6 years, so you know, you went and you bought that $2,000 car or that $2,000 engagement ring or whatever, and you left this sitting on the card for 18% for 6 years and didn't make any payments, you would actually still owe $5,399.11, and that's if there's no late fees because you didn't make any payments.